Hey, John here. We're at part 2 of bringing our SD card online. So this is the final step here. We're going to talk about how to actually transfer blocks of data into and out of the SD card so we can start working on implementing a file system and loading code into the SD card. All right. So hopefully we all recognize this. This is the Hello application running on our SD card. Comes from this repo here. There'll be links to all this stuff below the video on YouTube. This is where we're going to be building the BIOS for a CPM operating system. Okay, so I'm in the where am I? I'm in the Hello directory. This is the source code of the app that you just saw running on the terminal from my Retro board. Okay, quick reminder, the app is very simple. It is loaded into memory at the address in the symbol marked as load base, which I set to C000. And it just simply runs out of there after the flash boot code, or in this case, the test routine, runs and reads it off the SD card and starts it going. My point is, at that point in time, the SIO and the CTC and anything else, the memory banks and all that stuff have already all been initialized. So there's really not much for this thing to do other than to print some messages and count, using the DE register as a counter, and it prints out, hello, and counts in hex, 1, 2, 3, 4, 5, yada, yada, yada. After each time it prints a message, it goes into a delay loop for a moment, and it goes back up and prints again. So this is just a simple endless loop that just keeps on saying hello. Now, to load it and make it run, I'm looking at the code here in the tests directory. And specifically, I'm looking at the SD test application. And what this is going to do, I already walked through a lot of this in the previous video. Go find the playlist and back up and watch those if you want to. What I've done is covered all the initialization routines already. So all we got to do now is just say, let's read a block off the card and put it into memory. In this example, what I'm going to do is I'm going to simply read the first block on the card, which is normally where your MBR is. So let me go back here to make sure that we all read the right notes, and I had to just fix this because there was an error on this page. So what happens is I'm in the test directory here. I want to go to the Hello application. All right, now there's two situations in here. I'm dealing with a situation down here. I did these two lines, plugged my SD card into my Raspberry Pi, and I've showed that in previous videos when we're talking about SPI and SD card initialization and how they work and all that stuff. And these are the two commands that I use to copy the binary image of the hello bin. If you assemble this program, okay, I copy it into SDA, which remember is the entire card. So this is actually the first physical block, or normally where the MBR would go if you had a normal SD card with the usual stuff in there, all right? But I don't want to do that for this test. All I want to do is get one block of data on the card, read it in, and recognize that it's working. So I'm going to put an executable program that we just saw above on the card, very first block. And then I'm going to go in here in tests, which we were just looking at a moment ago, and I'm going to run this sdtest.asm program. And we'll see this in a moment. What it does is it goes and reads block number 0, which is where commands I just showed you, and put the executable hello app. It's going to read it into the memory at address C000. And as soon as it's done with that, it's going to branch to it and start running it. Okay? Now, there's two test apps in here. One of them tests the SPI. We've already gone over that. This one is the one that we use to test the SD card. All right, so this is the command that I ran to program the flash on my Retro board, which is what you saw running. Okay, now with all that in mind, let's take a look at the SD test app that we're going to use to do the tests. Oops, it might be better if I look at the source code rather than the binary. All righty, here we go. And I've talked about this a lot. This runs out of the flash, so it does the usual thing. Copy itself into memory. By the way, there's a special case for the stack pointer in here. Stack pointer is not initialized to 0 like it is in other applications I've written. It's set to this load base address, which is C000, which comes from the memory ASM include file up there. I set it to C000 because this is the first version of the bootloader that will read data off the SD card and overwrite all the memory starting at C000 and up to FFFF. So the last thing you want to do is have your stack anywhere between C000 and FFFF. So by setting the stack to C000 right here, we'll keep it out of that range. All right, and this is a safe place to put it. It's not going to be in bank switched memory or anything like that either. So this is a safe place for us to play around with right now. This initializes the usual stuff, prints some messages, calls this function called test SD, which is right below here. Okay. It does a bunch of initialization stuff I talked about in the last video. Okay. And when it's all done initializing, it comes down here and says, I need to load block number 0. Normally that would be the MBR again, remember, into memory at load base, which is C000. Then, if that works correctly, it's going to come down here and it's going to dump it all out in hex, and then it's just going to jump there and take a Hail Mary pass. Hopefully that's valid code, and I'm just going to execute it. Okay, so this is the whole program we're going to look at today, and this subroutine right here. Okay, so what do we do here? Now this thing is a little different than the stuff that came before because SD cards have a 32-bit block number, and depending on the context of the dock, it might be called a sector number or whatever. Okay, be careful as we get into the operating system stuff, sectors and blocks and logical blocks and all these words will be overloaded. Okay, so be careful about how you're thinking about these. Right now there's no operating system, so sector, block, those words mean the same thing in this context. Okay, so what am I doing here? How do you pass the 32-bit value to a subroutine on a machine that only has 8-bit registers and 16-bit register pairs? Now I could store half of the value in one register pair and half in another pair, and maybe that would have been a good idea. I don't know. What I decided to do is do something a little bit more modern and push a 32-bit value into the stack and use the value in the stack as a mechanism of passing a parameter to a subroutine. And we'll look at that on the other side of the fence in a minute. But since I want to read sector number 0, what I need to do is put a 32-bit value of zeros in the stack. So if I put 0 in HL register and push it twice, that's 4 bytes or 32 bits of 0 in the stack. No problem. And I mentioned high half, low half. Normally, if you're going to read a specific sector number or a specific SD block number, as I like to say, you need to make sure that you know whether it's big endian or little endian when it's in memory. And the answer is, I want to pass the value into the subroutine as a little endian value. And this is going to be annoying because when we look at the subroutine, it needs to convert it to a big endian value because that's what the SD card wants. Now, keeping it little endian on the code that calls the SD read block function, which is command number 17, is going to make our lives easier a little bit later since we're on a little endian machine and we need to be able to do little endian math and things like that. That's why this may seem pointless right now, but I'm looking ahead towards what we want to do with it later on when we're playing around with our BIOS and stuff like that. Okay, so what are we going to do? We're going to put a 32-bit value that equals 0 into our stack to pass it in as our block number. Then we're going to put in the DE register the address of where we want that data to be copied into our memory. This is our memory buffer address, where the sector that we're going to get out of the SD card, where we want it to be stored. We call command 17, and we're good. Now, because we put something on the stack here, someone has to clean it up. And that's us. And when we come back from command 17, we need to clean up our stack. All right? Now, in theory, you could leave it messed up, but that could lead to a whole nother bunch of problems. So if we're going to push 32 bits on, we got to pop it back off after we get back from the subroutine. When all that is said and done, this subroutine will return a 0 in the accumulator if it worked okay, and a non-zero value if it failed. Okay, so if it works okay, we're good. We jump down here, say, hey, everything looks good, and we dump out the buffer so we can see it, and we run it. If it doesn't work, we print out, that things didn't go well, return back to the caller, which you might remember from the last video is up here. If the test SD returns for any reason, there's many reasons it could return, because there's a whole slew of initialization that we went over last time. If any of the initialization fails, or this block can't be read off the SD card, it'll come up here and it'll gripe and says, oh, it failed, and just sit there and seize. Okay? So this is the high-level code. The driver is in the library, SD something or other.asm, like SD card, there it is, SD card.asm. Now I'm going to turn on the debugging here. Normally I leave it off because this is what's in the repo, but I'm going to turn it on. By turning it on, we're going to see all kinds of status coming out, and we can see what this thing is doing while it runs. And we're looking at command 17 right now, and all the commands is a little document in all capitals. I wrote, here's command 17, so you can easily find it if you search for CMD 17 in all caps like this, right? Now, here's the structure of what's going on. I'm going to set the SSEL equal to true. I'm going to send a command. I'm going to get an acknowledgement. This is like it's actually going to be an R1 style response. Okay? But there's more work to do. I then have to wait for the card to get the data off the flash inside of the card, put it into its buffer, and then send it back. So there's going to be some waiting after the acknowledgement. Okay, the acknowledgement means I saw your command. Give me a moment. Okay, wait for it to do its job, and then it'll give you, it's called a data token. That's the name from the SD spec. Once we see that, we know the next 512 bytes, because that's the size of a block. You can have any size you want as long as it's 512, right? It's an old Henry Ford joke. You can have any color you want in a Model T. You can have any color you want as long as it's black, okay? This only works for 512-byte blocks. So we're going to read 512 in here. Then we're going to get a 16-bit CRC value. And we're going to see that I'm going to just throw that away. Some other time we'll figure out how to validate it later on. And once we're done with that, we can set SSEL false, and we're all done. If all goes well, I set the accumulator to 0 and return. If something bad happened, I set the accumulator to 1 and return. Okay? We clobber a few registers. So let's see what's going on here. All right. So this comment over here is to help me remember where everything is. Now remember, when you call a subroutine, the call instruction stores the return address on the stack. So when when this function first enters, what we know is on the stack, the address that's in the stack pointer register is a 16-bit value that equals the address where we're supposed to go when we're done with this subroutine. That's what the return instruction does. It pops the address off the stack and puts it into the program counter. Okay? Now, before we called this subroutine, we pushed on a 4-byte value with the block number in it. Okay? So this is at the top of the stack. 2 bytes greater than that is a 4-byte value with a block number on it. Now, I want to not destroy all these registers, so I'm going to push BC, HL, I, all these registers, okay? So over here, I kept a tally of where everything is. This is going to be really useful later on. So don't mess with these things. At the address in the stack pointer plus 0, in this stack frame, we say, is where the DE register will be stored. And because that's where we put the target buffer address, where we want to put the data from the SD card, I'd make a note. I go, by the way, that's 0 bytes into the stack pointed by the SP register. This is at +2, that's at +4, that's at +6. These are not interesting to the subroutine here because I just wanted to save them because I'm going to clobber them otherwise. All right. If you go 8 bytes into the stack, that's the return address, and 10 bytes into the stack is where our block number will be found. We need that because we need to send it to the SD card. So how are we going to make all this work? Okay. What I'm going to do is I'm going to load the index Y register with a memory buffer called scratch. It's at the end of this file. It just says define storage 6. So it's just a 6-byte buffer. Then I'm going to load the index X register with 10 in decimal. Why? Because 10 is where this thing is relative to the stack pointer. Then I'm going to add the stack pointer to the index register, leaving the address now of where this is in memory in the index X register in IX, okay? So IY points to the buffer that I'm going to use to create a new command. Remember our 6-byte command that I'm going to send to the SD card. In that command, we're going to have to put the block number, okay? And the block number is the address of the block number that's stored in little endian byte order is now in the index X register. So how am I going to do this? I need to make a 6-byte command. It's got to be command number 17 because that's what the spec says to use to read a block. So I'm going to do the 17 and I'm going to play the game with the most significant bits. We've seen this before. I need to put that byte in the command buffer. I can't hard code this command like we did the other ones because I have to replace the block number, and that's what this is going to do. So I'm going to put in the buffer the 17 with the magic bits, okay? And that's at IY plus 0. All right, and this is in parentheses, so what we're doing is we're going to take in the address in the IY register plus 0, and this says go into memory at that location and store this value there, okay? Then I'm going to say load the accumulator with the value in memory at the address in the IX register plus 3. Now, IX, remember, is pointing at our block number here, right? That's what the comment says right there. And IX plus 3 is where the most significant byte is on a little endian 32-bit value. And I need to store it in our buffer into the second byte. So this is IY plus 1. And it needs to be, the big endian. So I need to put the big endian at the low address in my command buffer while I'm reading it from the higher of the 4-byte addresses in my from my input of the value in the stack, okay? So if you look in here, it's IY plus 0, IY plus 1, plus 2, plus 3, plus 4, plus 5. What am I doing? I'm walking through memory using index register Y, which points at the buffer I want to fill in 1 byte at a time. First byte, second byte, and so on, okay? Now, some of them are hard-coded. Command 17, please. And here's the CRC with the least significant bit, please. You saw all that last time. The other 4 bytes are go get them 1 at a time. Most significant byte, the next one, and so on. So while IY has the plus 1, 2, 3, 4, 5, the IX has the 3, 2, 1, 0. Okay? This is reversing the order of those bytes. Okay? When I'm done with that, I have a command buffer that I could send to the SD card that has the command 17 and the block number that I passed into the subroutine in it. I can print out some debug in here and say, hey, here's the stuff I want to send. We've seen all this before. I'll leave this as a task for the viewer. The one thing in here that's important that you see clowning around a little bit is that the DE register, which is stored at the top of the stack, we say, stack pointer plus 0, is the address of the target buffer. We won't use that until later, okay? So we have to make sure that we keep track of where it is because we're going to clobber the DE register, okay? And we need to be able to get it back. So what's going on in here? I'm going to dump out some debug here and print out the command and all that stuff and say, oh, by the way, the target address where this is going to go is going to be, I can grab DE, put it back into the stack. All right, I want to peek at it. I don't want to destroy it yet. And then I can dump it out down here, right? In the usual way that a lot of the debug works, you've already seen. Then I can turn on SSEL. What am I doing here? I want to push IY and pop a HL. This is me copying the value in the IY register into the HL register by using the stack, okay? When it's all said and done, the stack is the same as it always was before. I just use it as a temporary storage. Load B was 6. That's the number of bytes in the command buffer. All the commands are always 6 bytes. And I call write stir like we've seen many times before to send it out to the card. Okay? Now notice I don't call, the subroutine that says, do an R1 command like we did on all the other examples in the last video. Okay? This one has to do it itself. It's turning on the SSEL. It writes the string out. It reads the R1 response. We talked about that to death in the last video. All right? And then we don't want to turn SSEL back off yet because we have a lot of other things we still need to do, okay? And that's why this is different. So we're going to read the R1 response. So far, so good. The same as we've always seen before, a little bit of debugging down here. When we're done with all that, we have to ask, did the command get accepted okay? Is the card willing to do a command 17 and to the extent that the card can validate the block number at this point in time, is that okay? If so, it'll return a 0 in the R1 response. And if it is 0, we assume we're okay and we go on to the next step. If it fails, gripe about it, and we'll see this goes back to the caller in the usual way that we've seen before with all the other commands, okay? If it's okay, what are we going to do? We have to wait while the card actually gets the data out of its flash, okay? So what we're going to do is, looks like in decimal, that would be 1024 times. We're going to go into a loop here, and we're going to just read bytes, one at a time. As I say over here in the spec, it says, look, while the card is getting ready to reply, it's always going to just send all binary ones. So if the byte that we get back when we're reading right now, at this point in time, is all binary ones, then we just sit tight and wait. Okay? So if it's not all ones, we move on because we might be getting our data, is what will happen there. So if it is all ones, we fall down in the loop, we count the number of iterations. If we're not done yet, if it hasn't timed out yet, we go back up to the loop and keep reading and reading and reading. Okay, so this is it reading and throwing away more bytes. This is a lot like what happens it is what happens when we do the R1 response thing, right? It's the same kind of logic up here in this read R1 response. I don't know where the heck is it. It's called right up here, right? Okay? In fact, in theory, you could sort of do that. You can even use that as a subroutine. However, we need to wait a lot longer, okay, when we're doing this command. All right, so I just put the loop right in here, all right? If it comes back with a non-zero value, we end up down here. We want to make sure that non-zero value is exactly FE, because the spec says it'll return FF over and over and over while it's working. It will then send FE, which is what the spec refers to as a data block token. Okay? If that's what I got, I'm looking really good, and I come down here to Mr. Token OK. If it's not, I did not time out, but I didn't get what I'm looking for, so I gripe about it, and then I go to the error routine, which returns to the caller, okay? So if I did get the data token marker at that time, I now can proceed to read all the data bytes one at a time for the 512 bytes that I'm going to get from the card. Where am I going to put them? That's where the DE register, remember, that is at the top of the stack right now, was passed into the subroutine. That's the address where we want to put it. So if I just pop HL and push it back in again, all right, because I want to keep the stack level the same. I don't want to have the stack shrinking while I'm in this routine. It makes the error exit and handlers and stuff like that easier to write, okay? I'll leave it to you to work it out. This could be optimized away if we wanted to. But I want to say, until this is fully debugged and everyone's happy with it, it's much easier to leave your stack consistent while the code runs, even if it's not as optimal as it could, in theory, be. Okay? So, what are we doing? We're sneaking a copy of the target address and we're putting it into the HL register. We're going to create a loop with a byte counter like you've seen many other times and set it to 512 in hex is 200. We're going to read 1 byte at a time, store it in a memory at the address of the target buffer, add 1 to the buffer address, and count the byte that we're reading in. And I have some fancy debugging here so we can see what we're doing while it's going. And when that's all said and done, we will what? We'll ask, did the byte counter reach 0? If it's not yet 0, we're going to go back up and read another byte, right? Because that's just fits on the screen here, right? So this is going to go back up here and read another one. Count it. Am I done? No. Go up here and so on, right? Every time I go through the loop, I'll leave this to the viewer. You've seen these debug dumps before. This is kind of a fancy schmancy one. This prints out 1 byte at a time as they are arriving off the SD card. And every time I read in 16 bytes, I want to put a carriage return in there so that it doesn't just spew all over the screen. That's what's going on in here, right? So what happens? If it's not done, it goes back and reads more bytes. When it is done reading all the bytes, I need to read a 16-bit CRC value. And I have a little note to myself, somebody should verify this. And at some point, maybe we'll work on a 16-bit CRC checker code if we want to. It might slow things down a lot. And I don't know if we want to do it or not. Hey, seriously, let me know if you have any wise ideas on how we could do this efficiently. It'd be nice to be able to verify these things, you know? I mean, you wouldn't want to get garbage data and then have the OS not know about it, kind of a situation. When we're done reading the CRC, we're finally done. We can shut off the SSEL and mark the accumulator as 0 and return by falling down in here where we clean up the stack and go back to caller. Here's the error handler routine, and this is why we want to make sure that all the right values are on the stack, no matter where this routine ultimately warps out of this thing. Because you can see there's many different reasons to go down here to the error routine, which again sets the SSEL false like it does anyway, but this time it sets the accumulator to 1 and branches up here to this done routine. So this is why we want to make sure there's always 4 things to be removed on the stack. Otherwise, some cases we have to remove 3, other ones you got to remove 4, and you would have to keep track of all that. By keeping the number of things in the stack balanced at all times, and the only discrepancy is this one right here, as far as I know, putting this back in the stack, and it allows us to have a clean and simple. It simplifies the code down here, right? So that's how you read in a block. Let's go ahead and compile it. Let's go ahead and burn it into the flash. And I'm going to bring this terminal window back in here so when the flash is programmed and the thing reboots, we can capture what it prints. And as soon as it does that, I'm going to hit Control A because in Minicom it'll freeze the screen. And we can see all the dumping in here. This is all the initialization stuff we talked about last time, right? The command 0, command 8, and then you go to 5541, 5541. These are the A command. Those go out in pairs, right? And then I print a little message, oh, by the way, it took 2 times for this to work. Otherwise, it could take many, many more times, right? The reason it only took 2 times, by the way, is because it takes forever to print all the debugging out. If I didn't have the debugging on, this would take more loop iterations to complete. Okay, I talked about that in the last video. Here's the command 58 asking, hey, is this card support, version 2, and is it an XCHC card? And there's a bit hiding right there in that byte, okay? That says, actually, no, where is it? Is it in this byte? I don't know. Go back and watch the other video. The value that comes back is hiding in this message here. Actually, I think it's hiding in there. Yeah, it is. This is the R1 status byte that's in the R3 response. And one of the bits in this thing indicates that it is, in fact, an HC card. And therefore, it's compatible with the protocol that I implemented in my driver. So this is one of the things you need to check before you move on to your command number 17. So we can see it printing out. This is a 51, and there's the 4-byte block number. Luckily, it is, in fact, 0. Otherwise, we'd have a weird situation on our hands. And there's the CRC that we did not use by default with the least significant bit set. So that all makes sense. Target address is C000. And the R1 response that we got when we sent the initial command 17 down there is 0, which is the correct value. So this is the order in which we're interacting with the card, remember. We send this command down there. This is an FYI comment. Then I got an R1 back from the card for the command 17. Then I waited for the data token. I got the data token, and every byte, one at a time, as I read them in, I'm printing them out in hex here. Okay? I may have to restart this. Let me reboot it. So we can see what's happening with the hex dumps and all that. Let me finish it, and then we can scroll back a little bit. Okay, so there it is when it's actually running the hello program. Let's watch the rest of the booting, right? So there's the command 17. It got an R1 of 0. It's dumping out all the bytes one at a time as it reads them. Okay? Now, you'll notice that this data goes for a while, and it ends with a, like, OD, OA, OO, C9. Okay? I happen to know this is the end of a printable. This is like the carriage return and line feed function, I think, out of the hex dump program. Because I think, because C9, I know, is a return instruction, return from subroutine, okay? So this is actually part of probably the hex dump library, okay? And that's the size of the whole program. It only needs that much, so I didn't even use the rest of the bytes in that block, okay? Now, when the SD test app returns from command 17, when command 17 returns, I should say, into our test app, we write out, the block has been read, yay, been read. And then we dump it out using hex dump so we can actually see the addresses and a little easier formatting on our eyes here, okay? And we can clearly see this matches what the bytes were that came out of the card. And then we know that the SD test app branches to C000 and starts executing this code right here, okay? Now, the odds that we go through all this rigmarole, put the executable program on the SD card, boot it up, copy the flash into the RAM, and all this other stuff, and have it accidentally, coincidentally, start printing out hello from the SD card. I mean, that's the, the monkeys typing on a typewriter and accidentally discovering Shakespeare or reproducing Shakespeare. No, there's a 0% chance that this happened by coincidence. All right. So we just read in a block and put it where we wanted it to go, and it did what we wanted it to do. This is awesome. At this point, we can go in and we can read in an MBR, and we can look around at the block numbers in the MBR, which are 32-bit values. We can take those out, and then we can create a command 17 that says, hey, I want to read the block that goes along with partition number 1, and maybe the next block, and so on, to read in multiple blocks to load the OS into the RAM. That's exactly what we're going to do when we write our bootloader that reads in the operating system from partition number 1 and so on, all right? So that's where we're heading. Let's finish the discussion about the SD driver by looking at the logic to write a sector. Now, we're not going to run it and play around with that until later on. Right now, it's all about reading. We won't need to write a block until we actually are messing around with our BIOS and stuff like that. If you want, you can write your own routine to test it. But I when I did my work and was first working on my BIOS and CPM and everything, I got a lot of mileage out of never writing to the SD card. Okay, it's very handy, by the way, to avoid writing anything to the SD card until you got all the reading and everything else perfect. And the reason for that is, if you never modify the contents of the SD card, you don't have to keep recreating it when you screw up the writing logic, okay? So, but like I said, it's a good time to get closure on here because it's very similar to the reading, and we can just run through it really quick here on the way out the door. So, command write block. You're going to see a lot of the same technique as when we did the reading above in command 17. What do? We set SSEL true, we send the command, we read the ACK back, and now we're sending data to the SD card, not the other way around. So we get to send the data token to the SD card and the data block to the SD card, just like it would have done. This is how we saw it in the reading, and it's just the other way around, okay? Now, we will have sent all the data to the card. The card now needs to verify that the data is good, okay, and that the block number is correct, and it needs to write it into the flash and all this other fun stuff. So that might take a little while. So we got to wait a little while. Now, I'm half lying. There's two phases here, and this is what's wonky about this. Up here, it's all basically the same thing, but in reverse of the read logic. But when we're done with the waiting for the write operation to complete, okay, we get a response token that has to end in basically a binary 5, okay? These are don't care bits, and these must be this exact error value. Otherwise, an error has taken place. And this is all described in section 7.3.3.1 in version 8.0 of the SD spec on PDF page number 281, okay? When we're done with all that, now this down here is debatable. What should we really do? And if there's any SD card experts out there, I want to hear from you. Now, what I'm going to do is I'm going to set the SSEL to false. And I then have a stub of code in there that does this, okay? Now, what happens is, when we're done with all this up here, the SD card has some housekeeping that it has to do. That it's still really messing around with the flash memory, and I mean, the SD card probably doesn't actually have 512 byte blocks in its physical internal structure. These days, the blocks inside the flash card might be really big, so it might actually have to like read it and then replace part of it and write it back out and do other wonky things, okay? And those take more time beyond the time that's reported up here. So you have to wait for your block to be ingested, then you have to wait for it to do its housekeeping, okay? And this is a little unusual. I totally missed this in my first draft, and nothing worked right. So you need to do this, and the reason it's separated out in my view here is because way down the road, we can defer this logic and improve the performance of our system. But if we do that, it complicates our BIOS and everything else we're doing. If we just stick this in here now and say, I don't care whether I can optimize this later on, just wait until everything's done, then our lives are a lot easier for now, okay? Or forever, actually. Yeah, but it might be that we could get some more performance out of playing some games here. So what I did is I put in some logic in here to say, wait for all the housekeeping to finish. And this is what we'll look at in a minute. It's pretty simple. And when all this is said and done, you can, if you want, and I didn't write it yet, you can send down a command 13 and get more information if anything bad happened during this phase. Okay, so look what's going on here. We send a command, and then, is the command okay? Yes. Then we send the data, and we say, is the data okay? Yes. And then it actually does some more stuff, and then we have to ask using a whole different command, did all that stuff go okay? Right? In a perfect world, we would do all of the above. In the code we're going to look at, I only just do this, and then I just cross my fingers and say, it's probably okay. All right. Okay, so that's the state of this driver as it is today as we are looking at it. So what do we got going on here? The same game with the stack and the block number in the stack hiding up here. Same stuff about getting the registers, the index registers set up and copying it in, building our command using the same buffer actually that we used in command 17. But this is of course 24, but otherwise everything else in here is the exact same. We have some debugging that comes out if you want. I set SSEL to true. I send the command out there in the usual way, read an R1 response in the usual way, and I make sure that A is 0. The R1 value should be 0, otherwise we got a problem and we complain and we return. If it's good, we come down here. And we are supposed to write out 8 clock ticks, so read 8, throw it away. Then we write the token the other way, right? Instead of reading it and checking for it, we write it, okay? We're going to put FE into the C register and call write 8. That's how we send a byte. Then we're going to send our 512 bytes out. Now, this is a little different technique of sneaking a peek at the buffer address that's in the stack, okay? So this stack is a little different than the other one. I should make these consistent. And this one, the DE register was pushed up here, and the note is that keep in mind that the target buffer address is actually 4 bytes into the stack. Keep in mind the block number up here is 10 bytes into the stack, and that down here the index register has the address of the block number at that point in the code. All right. So with all this in your mind at once, where is where is the buffer address? And how do I get to it? Well, it turns out that it's at 5 and 6 bytes below, not above the stack pointer, but below the place where the buffer address is in the stack. So I can use the index register value that I know that it still points up here to SP plus 10, okay? And I want to know where, SP plus 4 and SP plus 5 are. Well, that would be 10 minus what? 5 and 6, right? And that's what you see in here, okay? It's used in the debug logic, and it's also used, where the heck is it? Where we were just looking. Here it is. So I can reach in there and steal it this way if I want to. All right, so just another technique. Then what am I doing here? I'm going to get my 512 byte counter into the BC register, and I'm going to have to save it, so I'm counting it and all that. And what do? I go get the bytes one at a time out of my buffer, and I'm going to write it, add one to the address, and then get the counter back, -1. If it's not 0, go and do it over and over and over. Okay, so that's it, writing out its bytes. I did not put in the debug logic to print them out one at a time like I did in the read logic. We can obviously cut and paste that in there if you really want to do it. When all that is done, remember I have to wait a while, and the spec says it could be up to 250 milliseconds. So what I'm going to do is just wait a long time, like 60,000 bytes, up to that many. I'm going to read one at a time, and if it's all binary ones, I'm going to fall down here, count it, and go into this loop, okay, and throw them away as they go. As soon as I get a byte that's not FF, I'm going to go down here to this DRC label, and I'm going to end it with this and ask if it's 5. So I'm really asking, do these bits equal 5? And I'm going to ignore the ones over here, because the spec says so. If that is in fact the case, then it looks like we're good. If it's not the case, I'm going to print out a message and gripe and return to the caller. So if it's good, we're done. Set SSEL back to false. All right? But we do have to wait for this busy situation to finish. And down here is where you might put the command 13 if you decide to go that route. So what does it mean to wait while it's busy? Okay? Well, what you need to do is you have to have SSEL on, first of all. And we can then read 1 byte at a time until we get a value that's not FF, right? Is that what that's doing? Too many negatives in here. Ask if it's all ones. If it's not all ones, stay busy. Okay, so yeah, it's is that right? I thought it was zeros. What am I doing? I'm reading this. Ask if it's FF. Oh, here we go. If it's not FF, I'm going to busy. I want to wait until it becomes all ones, okay? It just so happens that when it's busy, I believe what it does is it sends all zeros. So that's why this loop works the way it does. So the card, once it's done, it will release the meso line and let it float, and it'll become FF and fall down here, shut off the SSEL, zero the accumulator and fall down into here and clean up the stack and go on its merry way. And the same thing happens down here. If there was a problem, I'm going to do this, and I'm going to set, put a 1 into the accumulator, jump back up here, clean up the stack, and go back to where it came from. And I snuck in an extra little error message down here if I ever terminate a write due to an error. All right, so we'll look at this later on when we actually use it, but it's going to be a while. We're going to boot up CPM and stuff like that first, but I just wanted to get closure on all this stuff. So there you got it. Have fun. Load up some programs and see if you can get your a standalone program like this Hello program to work. And if you want to, you can start ahead on the logic that's in, where is it? Let's go back to the website here. This one. So the SD test app in here is what I did is I just copied this boot firmware out of here and I made it simpler. Okay, the boot firmware. Go ahead and poke around in here. It's the exact same sort of thing. They may have diverged, but what happens is you can see down here. Here's the load base. Logic we just looked at to read in a block, okay? And then what happens is rather than just jumping in and executing that code, oops, I'm lying. I'm still up here in the A command 41, yada, yada, yada. And then here we go. Instead of reading in an executable program, what I'm going to do is I'm going to read in a block from sectors. You can see here's SD card, and here's the 2 pushes that puts the 0 into the stack for the 32-bit value. I'm reading it into the load base, and I'm going to go. This is exactly the code we looked at right now. That's the code we looked at right now. But rather than blindly jumping to it like the test app does, I'm going to treat it as an MBR. And here I'm going to dump it out in some debug code. Down here, I got a comment. Somebody should verify that it's actually legal before we assume it is. So another room for improvement there. Then I'm going to set up an index register, and I'm going to actually dump out some more debug stuff down here. And eventually, I'm going to say, where is the first partition? And it turns out it's located at, this address offset from the load base is really where it is. And I'm going to go in there and I'm going to grab the 4 bytes out of the MBR and I'm going to push them into the stack because I want to read that. That is the first block of the first partition on our drive. That I'm going to read in to my memory, and I'm going to execute that. All right. Instead of reading the whole, just the raw card, I want to basically read in the data off the first partition. All right. And there's some more debugging in here, a lot of debugging in here, and this call read blocks thing here. What it's going to do is it's going to go into a loop. Where is it? This thing is going to go into a loop and read, I think, 32 blocks in a loop. So if you go down here, it'll read blocks. It'll be a counter. And what am I doing? This is, again, making the 32-bit value on the stack. And then it's going to call, this is commented out. One at a time, it's going to then, I'm going to print a dot so I can watch it go when it boots. And it's going to do some debugging that's commented out. And there's my 17. So I got a loop here that's going to just keep on calling command 17, command 17. When it's done with the command 17, I'm going to count the block. If I'm done, I go to success. And that's going to cause it to branch in and run the code. Otherwise, what I'm going to do is what do I want to do? I'm going to count to the next block in memory using this right here. Remember, I got 4 bytes in memory that represents the block address, and I want to add 1 to it. So what I'm going to do is I'm going to add 1 to the least significant byte. If there's a carry, All right, the value would become 0. And if that becomes 0, I got to deal with a carry. So I have to manually add the carry to the next byte and then do it again and again and again, right? So deal with the carries while adding one to a 32-bit value, okay? And I then go back to the top of the loop if I'm not yet done, right? So what happens here? I add 1 to the what am I doing? I'm incrementing the target address by 512. Remember, the target address is in the DE register pair. So by adding 1 to D, I'm really adding 256 to the DE pair. And I do that twice. I really incremented then DE by 512. All right, the games you got to play with an 8-bit system. All right, so what's the read block end? That should go back up to my loop. There it is. And read the next one and the next one and so on. So this will go until, honestly, I don't know how the heck the counter works. It's counter's up here. The B register has the number of blocks in it. DE has the buffer address, and the value in memory that IY points to is the block number that I want to read. So there's the loop there. I then say what? RB success must be when I'm done. Where's the check here? Yada, yada, yada. Yeah, if it goes there, it goes to success, and I XOR A. This actually will set A equal to 0. Why I need to do that in here, I don't recall. If it fails, I go back to the caller. I know why. Because this doesn't call. This doesn't jump into and execute the code that has been read in. This only reads the data into the memory. Okay? And it'll either return a 0 in the accumulator or a non-zero value in the accumulator. This will clean up the stack mess and go back to the caller. And then when this is like read blocks or something like that, right? No, there's boot SD. That's the whole thing. Dagnabbit. Where's read blocks? When read blocks is done, I don't know. Here it is. When that's the subroutine we were just looking at. We print out. What are we going to do? We're going to print out some stuff that said, "Here's what I did and where they all went." I wish I could keep track of I need extra windows or something. There's the subroutine we were just looking at. I'm sorry. The other stuff was debugging and printing and all that other fun stuff. I have to clean up my stack if I care, because I'm going to just warp into it anyway. But I'll clean it up to be a nice person. What do? I OR A. If A was 0 when it came back from this subroutine, and I do this, it will set the 0 flag, which when A is 0, remember it succeeds. So therefore I said jump if 0 to load base and run the program. If A was not 0, this would not happen, and I would print out an error message and go back to the caller. All right, so there you go. There's the entire boot flash boot ROM code, and in here the README files talk about how you can put the Hello app into partition number 1, like this if you want to, and boot it with the formal bootloader if you want. This one down here puts it into block number 0 with no MBR or anything at all, which we just saw, and it's suitable for booting with the test boot. Okay, so this one up here is the firmware, and this is the real firmware for the boot ROM. Okay, so you got both versions. You can see the difference. Obviously, I copy the real deal. Needs it to be in partition 1. The test case puts it in the raw card. Earlier on, we talked about SD cards in general. If you do this to your card, remember, you have no partitions at all. So you can't do this, right? Unless you go back up here. If you're going to use the same card, like if I use the same card I just did the test on that I just ran, I'm going to have to go through this process up here, and I'm going to have to partition my card in order to create a partition on the card so that I can write my test program into partition 1 on my card. using the dd command. Okay, so remember, there's a couple of balls in the air here. You know, what are you doing? Are you going to boot off the raw card? Are you going to boot off of partition 1, and so on? Now, the interesting thing is that the hello program doesn't care where it boots from. The issue in here is, where do I put it on the card? Does it go into partition 1, or does it go onto the raw card itself? Okay, so with that, you can now experiment with the test routine. You can actually play around with a formal bootloader and everything else. You got everything you need. The next step is, let's start working on a CP/M BIOS and boot up an operating system. So, thanks for watching. Next time, we move on to operating system hacking. See you then.